Okay, Calc kids, this is section 2.7. This is probably one of the more important sections in this whole first semester of Calc, because this is where we go from the limit discussion that we've been having to derivatives, okay, and how they're connected. So I'm going to go through the PowerPoint. This section is actually going to have a couple of different um, if I could get it to advance. Um, this is either going to be one very long video or I may break it up into two different videos. But I did want to kind of quickly go over the PowerPoint to try to explain where these derivatives come from and what they mean in relation to limits. And then I'm going to do some example problems from your homework. Okay, so derivatives and rates of change. So it says the problem of finding the tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit. So this special type of limit is called a derivative, and we will see that it can be interpreted as a rate of change in any of the natural or social sciences or engineering. So this leads perfectly into engineering and even physics and stuff. So let's first talk tangents. Um, if a curve C has equation y equals f of x, and we want to find a tangent line. Now let me back up. Tangent lines are lines that just touch a curve at a point. Okay, so if I had some curve and I wanted to find the tangent line to that at that point, it would just be a line that just touches it. Okay. Says we want to find a tangent line to C at the point P, then we consider a nearby point Q and compute the slope of the secant line PQ. Now, if you remember secant lines, they like go through a curve and hit it in two places. Okay, so first of all, want to point out this is our slope formula, right? This is change in y. This is like y2 minus y1 over x2 minus x1. That's slope. Okay, and remember m is always slope. So this is just the slope of secant line PQ. That's where the little subscript PQ comes from. Then we let Q approach P along the curve C by letting X approach A. So remember, the A is the X value of the point we're actually trying to find the tangent line at. The X is the X value that we're using and getting closer and closer to A. Okay, so one of the reasons I wanted to go over the PowerPoints is they have some nice pictures. So if we have this curved line, okay, this right here is the point that we are trying to find the tangent line to. Okay, but it says if the slope of line PQ approaches a number m, then we define the tangent T to be the line through P with slope m. Okay, it says this amounts to saying that the tangent line is the limiting position of the secant line. So essentially, this is the point Q that they want getting closer and closer and closer to this point P. Okay, so as this gets closer and closer and closer, what are my slopes going to be? Okay, so you can see, again, if this is my P and this is my Q, as Q moves, as I get closer and closer and closer, if I had another one there, okay, as I got closer and closer and closer to my point P, what's happening to the slope of my tangent line? As Q moves along the curve and gets closer to P, what's happening to my tangent line? Okay, or the slope of my tangent, I should say. So this is a biggie, okay? So this is the limit, okay? That's why we spent several sections talking about limits. The limit as x approaches A. Again, this is an equation for slope. This is definition 1. The tangent line to the curve y equals f of x at the point P, which is A comma f of A, is the line through P with slope, blah, blah, blah. The limit as x approaches A of f of x minus f of a over x minus a. Again, slope formula. Y2 minus y1 all over x2 minus x1, provided that the limit exists. So again, what they're saying is as this x value, so this would be my a value, okay? This would be my x value as x approaches a. That's what that limit is saying. As x approaches a, as it gets closer and closer to a, okay? That's how we find the slope of our tangent line, okay? So that definition is extremely important. So find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Now, we have several of these in our homework for today. So here we have an a equals 1 and f of x equals x squared. So if we use their definition 1 that we had, okay, a couple slides ago, then this is what we have. F of x minus f of a, which in this case is 1, over x minus a. Again, a is 1, as x approaches 1. So we've got to find these values out. So what's going to happen here is we're going to factor the top. Okay, we've got to solve this limit. So they factored the top. Then what happens? You can cancel, right? I go back here. You can cancel those, right? So then you're just left with limit as x approaches 1 of x plus 1, which is obviously going to be 2. So then 2 is the slope of my line. Okay, that's this, whoops, delayed reaction. So using the point slope form of the equation of the line, we find that an equation of the tangent line is blah, blah, blah. Do you all remember the point slope form of a line? Point slope form is y minus y1 equals m times x minus x1. And x1, y1 are your point coordinates. I hope that rings a bell back from like algebra 1. Y minus y1 equals m times x minus x1. That's the point slope form. Okay, so that's what they did down there. Our slope was 2. This right here was my 2 that I just found here. Okay, and then we use the point 1, 1. Okay, we sometimes refer to the slope of the tangent line to the curve at a point as the slope of the curve at that point. So again, what they're going to do here is kind of zoom in. If we had our graphing calculator, if we were using Desmos, okay, you can see here this curve. This is the x squared curve, and you can see the curve, okay, it's curved. But notice here we go by 2s. Actually, it looks like we're going by halves, but 2 on the x, 2 on the y. Okay, now we're going 1.5, so we're zooming in a little more. Now you can just barely see the curve of the line. It's not straight, but the more we zoom in, now we're 1.1 to 1.1, it almost looks straight. Okay, so the more we zoom in, the straighter that looks. The curve becomes almost indistinguishable from its tangent line. There is another expression for the slope of a tangent line that is sometimes easier to use. It's not, there we go. So if h equals x minus a, then x equals a plus h. Okay, so what they're talking about, this definition is sometimes easier to use. So essentially, h is the difference between the starting point and the ending point of where we were going from like point Q to point P. Okay, x was our x value for point Q, and a was supposed to be the end point, point P, that we were looking for. So h is the difference, okay, between the x and the a point. That's what they're getting at. So f of a plus h minus f of a all over h. Okay, same. It kind of depends on the problem which one you want to use, but it's essentially the exact same definition as definition 1 that we had earlier. Okay, so again, here's the important part. This right down here, your h is the difference in your x coordinates from the point you're approaching, which is our P, and your starting point. Okay, over here, h is your difference. You see this? Okay, this is h. So as h gets small, okay, as h gets small, so as h approaches 0 is essentially what we're after here, okay, as q approaches p or as h approaches 0. So here's, again, same thing, okay, what I just said though, limit as h approaches 0. Okay, so as q approaches p, the difference between the x values gets smaller and smaller and smaller. That's what h is. Okay, velocities. How does this translate to like real world velocities? In general, suppose an object moves along a straight line according to an equation of motion, s equals f of t, where s is the displacement or directed distance of the object from the origin at time t. The function f that describes the motion is called the position function. Okay, position function is almost always denoted by s of t. Okay, position function in calc and above is almost always denoted by s of t. In the time interval from t equals a to t equals a plus h, okay, change in position is f of a plus h minus f of a. So again, h is the difference, okay, in your time. So again, this from here to here, this is my h, okay? So again, this is, you can tell here, this is your f of a, this is your f of a plus h. That means, so this is like your a point, this is your a plus h point, okay? H is the difference between the two. So the average velocity over this time interval is, again, displacement, the change in your position over time. Okay, so that looks exactly like the slope formula we just had earlier. Velocity is the same thing as slope. So again, we're going to be looking as h approaches 0. Okay, as the difference gets smaller and smaller. Again, here's my h. Okay, as h approaches 0, which is the same as the slope of the secant line PQ. So again, velocity, same as slope. Okay, so we have, essentially we have the exact same definition here. Now it's just called something different. So now V of A is velocity at point A, or instantaneous velocity. Okay, instantaneous velocity. This is the exact same limit function or limit definition that we had for slope. Exact same thing. Okay, this means that the velocity at time t equals a is equal to the slope of the tangent time at p. I want to underscore that. This means that the velocity at time t equals a is equal to the slope of the tangent line at p. Okay, velocity and slope, same thing. Suppose that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. I think that's that thing that looks like the Space Needle in Toronto. Don't quote me on that though. What is the velocity of the ball after 5 seconds, and how fast is the ball traveling when it hits the ground? Now, solution, we will need to find the velocity both when t equals 5 and when the ball hits the ground. So it's efficient to start by finding the velocity at a general time t. Okay, so if we find the velocity for any time, so we just use t, we don't put in a real number yet, okay, then once we find the velocity formula, if you will, then we can plug in t equals 5 and then t when the ball hits the ground, okay? So using the equation of motions, s equals f of t equals 4.9 t squared. Now this, okay, is a general function. 4.9 t squared is your equation of motion. That's when you're dealing with meters. If I'm not mistaken, it's 16 t squared if you're dealing with feet. It's 4.9 if you're dealing with meters. Okay, that's a pretty standard equation, equation of motion. Okay, that's one you probably ought to kind of remember in the back of your mind. So the velocity then, okay, we have to find this h as h approaches 0 of f of t plus h minus f of t all over h. Okay, so we're literally going to be poking t plus h into the formula, t into the formula, and then solving that as h approaches 0. So getting right to it, again, here we plugged in the t plus h. Here we just plugged in the regular t. Okay, so we actually have to FOIL this out, okay? This has to be FOILed out, t plus h times t plus h. And that's what we did, okay? Notice they also went ahead and factored out, I hope you all can see that, they factored out this 4.9. So then notice over here is just this minus t squared part is right here, okay? So this part right here is the t plus h squared. So they pulled the 4.9 out in front. Okay, hope you all can see that. So then what do you see is going to happen? You all can see here that my t squared and negative t squared are going to cancel, right? So then I've got the 4.9 to 2th plus h squared. Then what happens here? I can actually factor out 1h out of all of these, right? Oh, actually, they factored the h out first. So notice they're going to take this and pull out an h and pull it out front. So they're going to factor an h out here. Then they're going to cancel this h. Okay. So now that's what we're left with. So as h approaches 0, then, as h approaches 0, this is just, all that's left is this part, which is 9.8 times t. As h approaches 0, that's all that's left. This is why, again, we spent so much time talking about limits and how to evaluate them. Okay, so 9.8 t, that is the general formula for slope or velocity, because remember, it's the same thing. Okay, so the velocity after 5 seconds is v of 5 equals 9.8 times 5. That's 49 meters per second. That's the velocity. Now, it says since the observation deck is 450 meters above the ground, the ball will hit the ground at the time t when s of t equals 450. They didn't tell us it was going to hit the ground after 8 seconds. Okay, they didn't tell us that. So we actually have to kind of solve for t to figure out what that is. Okay, so if it's 450 meters above the ground, again, this was our original position function. Okay, equals, that's how tall the tower was. So then if we solve for t squared, okay, it's approximately 9.6 seconds. Okay, now notice that when we typically solve for a square, we typically have like t equals plus or minus this, right? Why don't I have plus or minus? Because can I have a negative time? No. Okay, so they just do the positive. We're talking about a word problem here. We don't have to worry about negative times. So 9.6 is approximately it. So then how do I find the velocity when it actually got to the ground? Okay, I plugged that value in. Now they went back and plugged in the exact. They didn't put in 9.6. They put in the square root of 450 divided by 4.9 into the velocity formula, and it's 94 meters per second. Now that's when it hit the ground. If you all remember, let me back up. What was the velocity at 5 seconds? Was 49 meters per second. The velocity when it hit the ground is much greater than that. Okay, it's 94. You all realize as something drops, it actually accelerates, right? The speed. Okay, the longer it's in the air, the faster it's going to go, the closer it gets to the ground. It accelerates. So what we've just done, finding slope and velocity, that is derivatives. Okay, derivatives are used all over calculus, okay, and beyond. But derivatives have so many applications in the real world. It's a little scary. But that is derivatives. So it says, we have seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. In fact, limits of the form that, okay, formula, arise whenever we calculate a rate of change in any of the sciences or engineering. Essentially, it's a rate of change, such as a rate of reaction in chemistry or a marginal cost in economics. Any rate of change is essentially slope. Back in algebra 1 or 2, we calculated rate of change, and it was essentially slope. Well, what they're saying is that's essentially a derivative. Okay? Since this type of limit occurs so widely, it is given a special name and notation. So here we go, the derivative of a function. Now, this is the big topic, essentially, for first semester in calc, is derivatives. Okay? This is it. This is a biggie. Okay? The derivative of a function f at a number a, denoted by, we say f prime of a. This little tick mark you see, it's kind of like the single quote or single apostrophe, I guess I should say, that's the formula as h approaches 0, okay, if this limit exists. Now, the other way to do that, if you don't want to think of it as the difference, as h getting closer to 0, you can think of it this way, the bottom definition, as x approaches a. So it's essentially the same thing, only the top one we're talking about h being the difference between x and a, so that difference getting closer to 0, or you can think of it in terms of x approaching a. Okay, both of those are the exact same thing. They're still essentially the definition of slope. Okay, the top one again, h is the difference between x and a. Okay, so as that difference gets smaller and smaller and smaller. Okay, so either one of those works. Now, find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. Okay, so again, we're going to use our definition. From definition 4, we have f prime of a. That's how it's said. Okay, f prime is the first derivative. Okay. I just want you all to know that's kind of how it's said in English. F prime of a, or first derivative of f, equals that. And that's typically using the h is really probably the norm that people use more than the x and a. They use the a and h. From definition 4, we have that. So what do we do with that? Okay, we apply it to our function. And this is where it gets ugly. Okay, so this a plus h is again going in place of x. This a is going in place of x. So a plus h squared, this is x squared minus 8 times x plus 9, minus, again, square brackets, and now we're putting a in place of x. Okay, this has to be FOILed out. Okay, so there is quite a bit of work here. It's not hard work, but there is quite a bit of work just doing the grunt arithmetic stuff. So if you FOIL all of this stuff out, distribute the negative, yada, 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 you'll see a bunch of this stuff cancels. So like this a squared is going to cancel with that a squared. This 9 is going to cancel with that 9. This 8a is going to cancel with that 8a. And so all we're really going to be left with are those 3 terms on top. 2ah plus h squared minus 8h all over h. And you will notice here that this h will end up canceling with an h from each term. Okay, I probably jumped the gun here a little bit. But again, that h cancels. Okay, so now what does that approach then as h approaches 0? It approaches 2a minus 8. Easy peasy. Okay, now that we know what the derivative is, now we can find the velocity at any point A, because we found the general equation for the velocity or the rate of change. So we can find it anytime. So it says we define the tangent line to the curve y equals f of x at the point P to be the line that passes through P and has slope m. Since by definition 4 this is the same as the derivative f prime of a, we can now say the following: the tangent line to y equals f of x at point A, or sorry, it's point P, but it's at when x equals a, is the line through a comma f of a, whose slope is equal to f prime. Okay, so f prime of a is essentially the same thing as the slope, okay, which is that limit function as h approaches 0 of f of a plus h minus f of a all over h. It's the same thing. Okay, same thing as slope. And then this is just the point slope form. Okay, if you remember the point slope form, this is y minus y1 equals m times x minus x1. That's all it is. Okay, point slope form. Now, a couple more little things in terminology here. Suppose y is a quantity that depends on another quantity x. Thus, y is a function of x, and we write y equals f of x. If x changes from x1 to x2, then the change in x, also called the increment of x, is, now, this symbol right here is the Greek delta, okay? And delta means change, okay? Just so you're aware of that. So mathematicians use that little delta symbol all the time. In fact, when I was learning slope, they did change in y over change in x. That's how my teacher years ago actually denoted it on the board. She didn't use y2 minus y1. It was change in y over change in x. Okay? And the corresponding change in y, of course, is delta y. So, kind of jump the gun again here. Whoa, what happened there? I don't know. So again, this is slope, right? This is slope. So the average rate of change of y with respect to x can be interpreted as the slope of the secant line PQ. So again, here's my change in x. Here's my change in y. Okay, slope. So again, yet another definition. Okay, so the instantaneous, that's kind of the key word here, instantaneous rate of change is the limit as the change in x approaches 0 of the slope, change in y over change in x. Okay, as the change in x approaches 0, which means it's kind of the same thing as saying as h approaches 0. As the difference gets smaller and smaller and smaller between the 2 points, that's where we get our derivative. So it says we recognize this limit as being the derivative f prime of x1. Okay, just more notation stuff. So the derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. So derivative f prime of a is the instantaneous rate of change of the function y equals f of x. Okay, at the point a. This means that when the derivative is large and therefore the curve is steep, as at the point P in figure 9, the y value changes rapidly. Okay, so we know that if we have like a slope of 3, that is a very steep line. Okay, so your difference in your y values is very large. When the derivative is small, the curve is relatively flat and the y values change slowly. Now, this is kind of important. So in other words, f prime of a, or the derivative of f at point A, is the velocity of the particle at time t equals a. F prime of A is the velocity of the particle at time t equals A. We already kind of knew that. Okay, derivative is the same thing as velocity, same thing as slope, rate of change. It all means the same thing. Here's what I think is important, because a lot of people kind of intermix, and I've done it myself, the words velocity and speed. Okay, speed is the absolute value of velocity. Okay, the speed of a particle is the absolute value of the velocity. Velocity, believe it or not, can sometimes be negative. Okay, all right, if you're slowing down, but the speed, all right, is the absolute value of velocity. Okay, so that's one that a lot of people get kind of screwed up on. Okay. A manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is C equals F of X dollars. So again, the cost depends on the number of yards of fabric you're producing, which makes sense. So what is the meaning of the derivative F prime? What are its units? In practical terms, what does it mean to say F prime of 1000 equals 9? And which do you think is greater, F prime of 50, F prime of 500? What about F prime of 5000? Now let's go through these one by one. What is the meaning of the derivative? If the cost is C, okay, and it depends on the yards produced, so it says the derivative F prime of X is the instantaneous rate of change of C with respect to X. That's the instantaneous rate of change with the respect to X means with respect to the number of yards you're producing, right? So it says that is F prime of X means the rate of change of the production cost with respect, okay, rate of change of the production cost with respect to the number of yards produced. Okay, rate of change of production cost with respect to the number of yards produced. Because F prime of X equals, this is the last kind of limit definition that we learned, limit as change of X approaches 0, change in cost over change in yards. Okay. The units for F prime of X are the same as the units for the difference quotient, change in cost over change in yards. Since delta C, the change in cost, is measured in dollars, and delta X in yards, it follows that the units for F prime of X are dollars per yard. We're talking cost based on yards produced, so dollars per yard. Okay, so my guess is, before we go any farther, that probably the cost per yard goes down the more yards you produce. That's my guess. Okay, so the statement that F prime 1000 equals 9 means that after 1000 yards of fabric have been manufactured, the rate at which the production cost is increasing at $9 a yard. So when they hit 1000 yards of fabric, it's going to cost them $9 a yard, or a total of $9,000 to produce that. Okay, C is increasing 9 times as fast as X. Okay, since change in X equals 1 is small compared with X equals 1000, we could use the approximation that F prime of 1000 equals change in C over change in X. Make the change in X 1, so then the change in C over 1 is just change in C, change in cost. We say that the cost of manufacturing the 1000th yard, or the 1001st, is about $9. The rate at which the production cost is increasing per yard is probably lower, that's what I was saying earlier, when X equals 500 than when X equals 50. The cost of making the 500th yard is less than the cost of the 50th yard because of the economies of scale. What they mean by that is, once you get your presses made and you get all that pre-work done, setting up the presses with the new design, the inks, figuring those out, blah, 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 blah. Once you get that done, the more you make, I'm guessing the cost per yard goes down. Okay, it's going to be way more expensive if you only make 1 or 2 yards of something than if you make 2,000 yards of it. The cost per yard, that is. Okay, the manufacturer makes more efficient use of the fixed costs of production. So F prime of 50 would be greater than F prime of 500. Again, it's going to cost more per yard to make 50 yards than it would 500. But as production expands, the resulting large-scale operation might become inefficient and there might be overtime costs. So I guess I hadn't really thought about that. That could be true. Thus, it is possible that the rate of increase of costs will eventually start to rise. So there's businessmen there's literally mathematicians that are hired by companies that kind of do these calculations. Okay, how many, yards of fabric can I make with my production costs being this? And then what's going to be that threshold when it starts to go up again? Okay, we can actually find the derivative, and then we can actually graph derivatives and figure out when those increase, and it gets pretty enlightening, I think. So it may happen that F prime of 5,000 is greater than F prime of 500. So you may get so high that you've got to pay overtime and then cost per yard goes up. Okay, I'm going to stop there because this is already long enough. And I am going to make a second video where I actually work on practice problems from the actual homework of 2.7. Okay, I wanted to take the time to go over the PowerPoint because this is the most important topic of first semester calc is derivatives. Okay, so this completes the PowerPoint explanation of 2.7.